In this video, we're going to be talking about the first section of the first unit, and this is called the Tools of Algebra. So today what we're going to be talking about is just the nature of numbers themselves. So we're going to be just talking about classifying numbers, and this should be a pretty short lesson. So first off, let's go ahead and take a look at some of the first definitions. At the bottom of the list, the most specific set of numbers is called the natural numbers. These are also known as the counting numbers. These are the numbers 1, 2, 3, etc., kind of like whole numbers. We'll talk about that in just a second. Natural numbers are denoted with this symbol right here, this kind of fancy script N, not just kind of your average everyday N. So we'll kind of maybe practice writing that in a way that kind of sets it apart. But at the end of the day, like if you put an N, like good enough. So those are known as natural numbers. Whole numbers are almost exactly the same thing, but it just includes the number 0. So a whole number is 0, 1, 2, 3, etc. All right. Integers, which have the symbol. Oh, by the way, back to whole numbers. There really isn't like a formal agreed upon symbol for whole numbers. But for our purposes, if we want to use kind of a fancy W, and I'm not sure I can draw a fancy W now that I say that, kind of like, something like this. That would be the symbol we can use for us. Because, as you may learn very quickly, us mathematicians, we are lazy. And if we can avoid using words and replace them with symbols, then that's what we're going to do. All right, next up is integers. Integers, which uses the symbol Z right here. And no, I do not know why it's a Z. The set of numbers containing both positive and negative whole numbers. So now we're not just talking about whole numbers here, which are just positives. Now with integers, we're talking about the set of numbers that includes making those whole numbers also negative. All right, so you can see some real overlap in all these concepts here. And then we get to kind of the last couple, which maybe you'll find a little more complicated. The definition certainly seems more complicated. So when we talk about rational numbers, we're talking about any number that can be written as a fraction. Rational is another name for fraction. So it can be written as a over b, where a and b are integers, and b cannot be 0. We'll kind of spend some time this year making sure we understand this concept that you cannot divide by 0, but that's a conversation for a different day. Written as a decimal, a rational number is either terminating or repeating. All right, so here's the deal. Lots of things are rational numbers. Rational numbers are anything that you can write as a over b. So pretty traditional, something like 3/4 is a rational number. 3/4 as a decimal is 0.75, also still a rational number because we can, where did this 0.75 come from? It came from doing 3 divided by 4. So I can represent this as a fraction of a over b, which makes it rational. A number like 1/3 obviously can be rational because I can write it as a fraction. 1 over 3 is a rational number. As a decimal, that's 0.3333, so it's 0.3 repeating. And again, if we look at this last sentence here, written as a decimal, a rational number is either terminating, like 0.75 is, it just ends, or it's a repeating decimal, 0.33333. Okay, so another one like, say, 0.6 repeating is rational because it's also just 2/3. Okay, so lots and lots and lots and almost everything is a rational number, including every number that we've mentioned above. So, for example, the number 7 is a rational number because I can write 7 as 7 over 1. So that means all natural numbers, all whole numbers, all integers are all types of rational numbers. They're just more specific types. Okay, so rational numbers are sort of like the all-encompassing name, and then you have different, breeds of numbers, if you will, uh, inside of that. All right, and then irrational numbers would then be numbers that cannot be written as fractions. So they cannot be written in the form of a over b. And for the most part, those come in a very specific style, which we can talk about just a second. The most common irrational number would be pi. And pi is a rational number, or is an irrational number, because it, as you hopefully have learned, is a non repeating, non terminating decimal. So we will approximate it and we'll say 3.14 maybe, but that's not really what it is. The symbol pi, the number pi, is a number that cannot be written as a fraction, and it is non-terminating and non-repeating. So it just goes on and on and on in what appears to be sort of a random fashion. Another common, you won't know it yet, it won't come till Algebra 2. There is another number known as E, which is approximately 2.718, but once again, it keeps on going. So those are two irrational numbers. But the most common irrational numbers that you're going to find are numbers that don't have a perfect square, that aren't perfect squares. So, for example, we would not consider the square root of 16 to be irrational, because the square root of 16 is 4, and 4, as we know, can be written as 4 over 1. So that would be a rational number. Also an integer, also a whole number, also a natural number. So this is not irrational. But compare that to a number like the square root of 3. There is no number that you can write as a rational number that, when squared, is 3. We can approximate it. We can write a long decimal for it, but it is irrational. So let me get approximately what it is here. So the square root of 3 is approximately 1.732050808, and then my calculator says, hey, that's good enough. But again, that continues. So I cannot write that as a ratio of two numbers, a over b. So that is an irrational number. Any square root that you can't do, so like the square root of 2 is also irrational, the square root of 7, the square root of 8, but the square root of 9 is not, because we can write that as 3 over 1. All right, so your most common irrational number that you're going to deal with are ones that are square roots of ones that you cannot solve into a regular, good old-fashioned rational number. The symbol for irrational number is actually, there isn't one, but since everything that's not rational is irrational, then oftentimes what you'll do is you'll have like negative q as the symbol for not q, right? Is it irrational or not rational? And so that would be the symbol for irrational numbers. And then the last one we're really going to talk about today is real numbers. And the real numbers is everything that we just talked about. So that's the set of all numbers. We're going to just pretend like, and I didn't really mean to use the word pretend. There is a thing called imaginary numbers, but we're going to cover that at a later date, probably Algebra 2. So there is something else coming in the future, but for now, let's just pretend like there isn't. And every number that exists is a real number. So whether it's irrational or rational, that they all make up the full set of real numbers. All right, so let's kind of look at this as a Venn diagram. Kind of see if this helps put things in their places. All right, so what I'm trying to illustrate here is everything inside the big rectangle that's cut into two, right? We're going to say that this is the set of all real numbers. And the symbol, the way I write the real numbers number symbol is the fancy superscript R thing, or not superscript, excuse me. I draw a vertical line, and then I draw an R over the top. All right, so what I'm trying to get you to see right there, and I'm going to erase this in a second, but real numbers, everything that's a real number will fit inside this box. Okay, so you name it, it goes in this box. Okay, now inside of real numbers, there are two types of numbers. There are rational numbers and there are irrational numbers. And there is nothing else. So that's what we have here. So this side of the box, this is where our rational numbers live. And here are our irrational numbers. Okay, and again, the symbol here is a Q, and the symbol here is not Q. Okay, so you name a number, 7. 7 belongs over here on the left side. The square root of 3 belongs on the right side. There is no overlap. All right. But 7 isn't just a rational number, it's other types of numbers as well. So within rational numbers, we have another designation, and the next biggest group would be integers. So this would be our integer group. And that is the Z. All right. So if I'd use the number 7, I'm going to erase it in a second because we're going to actually put it somewhere else. 7 is an integer, so it fits within this big circle here. All of this, right? Everything in here is in the world of integers. So 7 goes in this circle. Oops. Didn't mean to do that. Okay. But some things are integers that are also other things. And what's the next category? And that would be whole numbers. And we kind of agreed we would use like a W for whole numbers. Well, 7 is not just a real number, or I'm sorry, well, let's go all the way down. 7 is a real number. That's why it's on the left side. 7 is a rational number. Actually, let me start over. 7 is a real number, which is why it's in the whole box. 7 can also be considered a rational number, 7 over 1, which is why it's on the left side. 7 is an integer. That's why it's inside the Z. But 7 is also a whole number, so not only should it be inside the Z, it should be inside the W. So we'll move 7 here. And then inside of whole numbers are things that are natural numbers. And we'll use an N for that. And 7 is not just all of those things, it's also a natural number. So by putting the 7 in the innermost circle, now we know it's natural, it's whole, it's integer, it's rational, and then obviously it's a real number. All right, so let's do another example. Let's say -2. -2 is a real number, so it's going to go in the box. It can be written as a fraction, -2 over 1, no problem. But it's also a positive or negative whole number. So I'm going to put it here with integer. It is not a whole number because whole numbers are only 0 and greater. And so -2 would go here. And this tells us that it's an integer, it's rational, and it's real. Okay. So let me throw a few numbers at you and have you place them. Pause the video and place them in the right spot. So I'm going to just kind of throw some numbers at you here. I'm going to say 2/3. Let's go with the square root of 16. Let's say -3/5. Let's say -1. And the square root of 2. All right. So all of these are real numbers. So by default, we're going to put them in these boxes. 2/3 can not be written as an integer. It is not a positive or negative whole number, but obviously it can be written as a fraction. So 2/3 belongs over on the rational side in the rational box, but not inside one of the circles. The square root of 16 is 4. 4 is rational, it's an integer, it's whole, and it's natural. So we can go ahead and put the 4 in here. Or, as given, the square root of 16. Negative 3/5. Yes, it's negative, but that's not an integer because it isn't a whole number. And so rational, so it's just going to fit here within rational. Negative 1. It's not natural, it's not whole, but negative 1 is an integer, which also makes it rational. The square root of 2 cannot be simplified. It's not 1. 1 times 1 is 1, not 2. So it cannot be written as a fraction. It is irrational, so it belongs all by itself over here. All right. And then what about 0? 0 is not natural, but it is a whole number. So 0 belongs here because it's whole. It is an integer. It's 0 over, any number. 0 divided by 2 is 0. So it can be written as a fraction. And therefore, it's inside the rational world. All right. Hopefully, this is all making sense. In fact, thinking about whole numbers, this Venn diagram is sort of misleading because it kind of implies, especially by the sizes involved of the circles, that there might be a lot of things that are whole numbers that aren't natural numbers. But in reality, 0 is the only number that would fit inside this circle that is whole that doesn't fit inside natural. Because any other number that's a whole number would actually also be classified as a natural number. And that's why, like 4 is a whole number, but more specifically, it's a natural number. 0 is the only one that would be all by itself. All right. Let's move on to the last little thing we're going to do. And I would like you to think about the following statements. Example number 1, using counterexamples. Is each statement true or false? If it is false, give a counterexample. Proving something false is very simple. You just have to find one example of it not being true, and then you can say the whole statement is false. Proving something is true is quite a bit more challenging because you have to show that it works for every single instance. But let's not get ahead of ourselves. All whole numbers are rational numbers, true or false. And that would be true. Every number that's a whole number is going to fit inside this whole number circle. Okay, everything is going to be inside of a whole number. And those all are contained within rational numbers. So quite clearly, I hope, this is a true statement. The square of a number is always greater than that number. There was one other thing I was going to talk about. We're saving it for another lesson, so I guess we can sort of delay on this. But since it's already here, let's go ahead and throw it out there and see if we can figure it out. If you square a number, it's always bigger than the original number. That would seem to be true. 2 squared equals 4, 3 squared equals 9. So we square the 2, it becomes a bigger number 4. But there are examples where that is not true. And one classic example would be a number between 0 and 1. If I take a number of 1/2 and square that, I get 1/4, which is smaller. So to prove something false, all I have to do is show one counterexample. And so 1/2 squared equals 1/4 would be an example of a counterexample. So this is false. Also, really not a question I meant to be asking. And then we get to part C. All whole numbers are integers. So every number you can call whole, can you also call it an integer? And the answer is yes, that is true. No fractions are whole numbers. True or false? So if I think of a traditional fraction like 3/4, that is definitely not a whole number. But a fraction could be unsimplified, and you could have something like 4/2. Definitely it's a fraction, but 4 over 2 simplifies to 2. And so 2 is a whole number, and so this would be false. Okay, and there's my counterexample right here. All right, like I said, a pretty short lesson today. We're going to keep it nice and simple for what is a Monday as I record this video. And if you have any questions about any of this, let's talk about it in class.